Hello. Welcome back to the Calculus 3 or Multivariate Calculus lecture series. My name is Sean Perry. Today we're going to be looking at an introduction to vectors. I am going to start with a quick overview and then launch into a more complete lecture. For right now, though, in case you don't have time for that, here's what you need to know. In Calculus 3, vectors are essentially going to be directed line segments based at the origin. They have a length and a direction. They can be added to one another by adding the coordinates that sort of represent those vectors. So here I have coordinates 1, 2, and there's a vector pointing from the origin to 1, 2. We use these sort of angular braces to describe the vector and distinguish it from a point. And then what can I do to add them together? Well, I can simply take the sum of their x components and get 2, and the sum of their y components and get 1. And this is the sum of the two vectors. Sort of if we had taken this one and started from the tip of this one and marched along until we got to their common endpoint. We can also scale vectors, which means multiply them by some constant. And that might make them longer, or if it's less than 1, it would make them shorter. If it was negative, it might reverse the direction. But essentially, again, we define the multiplication component-wise, so that it's just a constant times a vector is the constant times each one of its components. And finally, we can calculate length using the Pythagorean theorem. Here I have it shown for just this two-dimensional vector field, but it extends nicely, and I'll show in the rest of the lecture how that works for 3 and n dimensions. But essentially, we just take the sum of the squares of the components and square root it, and this is our length. We use a double absolute value to distinguish the norm of a vector versus the absolute value of a number. So here's an overview of what I plan on lecturing on today. We'll start with some background concepts. Things like coordinates in n-dimensional Euclidean space and other things you might need to know to understand vectors, even in their informal definition. So informal, in this case, just means sort of less rigorous but easier to grasp. Things like the idea of vectors as arrows or as directed line segments. So these informal, we'll call them definitions, are just going to be sort of ways to approach vectors. There is a formal definition, but this might be a little bit underwhelming for some people because it really just has to do with a set of all things which obey a certain collection of properties. And those properties become assumptions about what is a vector. So this is going to relate directly to properties of vectors. So to begin with, let's talk about points in space. And here, when I say space, let's clarify that I mean a space of numbers. So one space that we're probably all familiar with is the real number line. It's a visualization of the real numbers as laid out on some line. We would call this R1, and we specify that the numbers we're talking about are so-called real numbers. We don't have to worry too much about the definition of a real number here. Let's just say it's all of the numbers that you might be interested in that fill up the space between the integers, between the rationals, and pretty much everything else which we might be interested in as a point lives on this line. And we might remark that there are some special points, right? Once I determine 0 and 1, I've told you which side is positive, and I've told you basically a scale about where you could mark your check marks. Now, if you tell me some point on this plane, could be anywhere, once you make these decisions about 0 and 1, this thing's value is fixed. But we could consider this one value as a point on the number line. What about R2? This is two number lines, and we pass them through each other's origin. So I can just call that the common 0. Again, once you start making decisions about where to place your ones, you've sort of frozen these lines. But notice there was some decisions to make. Here I could have put my ones over here, would make just as much sense. Some people are very used to the idea of left is negative, right is positive, up is positive, down is negative. But these are all decisions you make as the mathematician drawing this picture. These are just the most common decisions to make. Let's put right positive. Let's put up positive. This is called the standard orientation of R2. And so now we might need to specify 2 points, an X and a Y, in order to pick out a single point on the whole surface of the plane. And we might call this the coordinate XY. This is really just a list of numbers, but not a set. Not a set of numbers. Remember, in a set, right, a set of two numbers, x, y, order does not matter. But in a coordinate, or a list of numbers, order does matter. So a list, or a coordinate, but not a set. And then, rather than draw this all over again, when we go to R3, we could just imagine adding another axis. However, the standard orientation would not be to draw it this way, to add another axis like this. So when I go to, let's erase enough. When I go to R3, we still will have another axis here. And you imagine this coming out of the board at you, perhaps. And the standard orientation is to say that this is X. Well, first of all, notice we need to mark a 1 on here. That'll determine the scaling, and that 0 is still the common intersection of all the axes. So we would mark X, we would mark this Y, and we would mark this Z. And the idea here, this is the quote-unquote standard orientation of R3. If we had flipped one of these, it would be a different kind of orientation. Perhaps isomorphic to the original one, but also perhaps not. Now, if we want to plot a point in this, often what we do is we make little perpendicular or parallel paths to the other axes to show, for example, what a point in the xy plane would look like. We might put it here. But then we could also imagine parallel transporting this z. Right? And in any case, what we're looking for is this point here. Right? Lots of different roads we could take to get there. We could walk along the z-axis first. We could walk along the x-axis by its length, and then walk into the page by the y-axis by its length. And you see there's kind of a whole cube's worth of paths that we could trace out in order to go from 0, 0 to xyz, the point in R3. But still, this is just one point sort of living in the third dimensional space. Oh, let me really quickly remark on the orientation property of R3. We usually figure that by the right-hand rule. If you put your fingers in the x direction, curl them in the y direction, z is your thumb. Another right-hand rule is if you put your thumb in the x direction, your index finger in the y direction, the middle finger at perpendicular is z. Right? Either way, it's to produce this this kind of orientation of the axes. Okay. And with Rn, so with Rn, this becomes somewhat more difficult to show. There are generally no really good ways when n is greater than 3 to draw 4 dimensions and compress them into the 2 dimensions of the page. So oftentimes what we'll see is just sort of a 2-dimensional one drawn, and then maybe several kind of indicated by some other axis. So they might call this x1, x2, and x3 to xn. Or maybe just ... xn. And we might only concern ourselves with the x1, x2 slice. Why not x, y, z? Well, we've run out of letters. And even if I were to go back through and pick new letters, well, n could be huge. There's nothing that keeps us from extending the logic of vector spaces to large dimensions of n. In fact, this is exactly what's required for certain kinds of problems. So how do you come up with that many letters? You don't. Instead, you would use a subscript. So, for example, when we have R1, we generally didn't need any kind of special notation because R1 is just like a regular number. For R2, we would use a coordinate notation to indicate a point. For R3, another. But for larger n, generally we'll just write x1, the first variable, x2, the second variable, and so on up to xn. And so this is something to keep in mind as you read more and more mathematics, that sometimes subscripts may not indicate the first and second variable of one kind, but two different variables of two different kinds, as different as x and y would be in the equation. This can get confusing. Index juggling is a huge notational problem, but this is going to be something to acclimate yourself to. Another thing I'd like to look at just briefly is a review of some of the properties of a number from algebra. So, for example, what does it mean to be commutative? Right? Commutative in the case of, say, addition or multiplication meant that u plus v was equal to v plus u, or that u times v was equal to v times u. What does it mean to be associative? It meant that u plus v plus w was equal to u plus v plus w. Make sure that's not screen. No, that looks good. And the same thing, of course, being true for multiplication, also an associative operation. And that there was a property which kind of ties together addition and addition and multiplication, the distributive property. Which says, that you can get around this order of operations issue by just doing your multiplication against both terms. Remember that we had special numbers in our algebra system. Specifically, we have an identity number. For addition, that identity number is 0. And for multiplication, it is 1. Adding by 0, multiplying by 1 doesn't change anything. And we had inverses for addition and multiplication. Namely, you could take negative x and add that to any x, and it would be 0. Or let's say negative u, keep with what I've got up here. Right? If you have u plus negative u, that's the additive identity. So we say that u has the inverse minus u. And likewise, we have 1 over u, as long as u's not 0, right? That would be a problem. But then u times 1 over u is 1, the multiplicative identity. So we have these things called inverses, which are ways to go from any element back to the additive or multiplicative identities. And we sort of also, I think it would be part of a good review to mention that we have certain properties of equality that make all of this true. But in all honesty, I think that's probably left for another video. I would love to do a video on sort of our foundations of mathematics, the axioms of equality, what goes into making equality functional by assumption, right? But again, for another time, perhaps. Now, the reason I wanted to go over all of this in such detail is because in the final part of this video, where we talk about what a vector is precisely, in its total generality, or at least in as much generality as I can put forward here, it's going to be based on these properties, right? It's going to be fulfilling these properties makes you a vector, or a vector space whose elements are vectors. But for right now, let's get back into the Calc 3 notion of a vector, so that we can talk about what kind of vectors you're going to see in the Calc 3 course. So the first thing I think is an intuitive place to go. Let's actually list the sort of intuitive notions of vectors that you're going to be exposed to. So vectors is informal. And again, informal because I'm not presenting definitions here per se, and also informal because these are examples of vectors and not vectors in general. So one way that we think about vectors, and we'll start with vectors in the plane and then talk a little bit more about vectors in R3 and Rn, is as arrows. These arrows have a length and they have a direction in which they point, right? And that completely typifies them as a vector. What I mean by that is that two arrows who are simply not in the same place, but have the same length and the same direction, slope that they're pointing in, would be considered the same vector, right? If this was u and this was v, then, and I'll try to give them their little hats to indicate when I'm talking about a vector, then actually these two are equal as vectors. We'll talk more about this as we go on. Let me not get too held up on that. We can also think about vectors in terms of directed line segments, right? If I just plopped a grid down here, and I said, okay, well, holding everything else the same, here are my vectors. So here they have starting points and end points, starting points and ending points, right? And they're distinguished because it's pointed towards the ending point. So these we would call directed line segments. And again, when we talk about it this way, there would be some kind of translational invariance. If you just kind of slid the vector around, it wouldn't be considered to be a different vector. And that's why I think it makes the most sense to start here with another notion, right, which is going to still be directed line segments. But based at the origin. And I think here's where you can get a good feel for how these vectors are going to go together, because it's no longer quite so obscure, that two vectors who aren't in the same place are equal. Now, if they are in the same place, they're equal. And only if. And so here's this guy translated down and put on the origin. This guy translated here. I'll try to keep that parallel, put at the origin. And two things. Well, number one, we're going to have a nice way now of talking about the addition of one vector to another. And another thing is that there is a one-to-one correspondence now with the coordinate system of this plane. Right? Here is a coordinate that it points to. And so now we can start to think a little bit more about this in terms of its components, right? In terms of the x and y coordinates given at the end points alone. No need to consider the initial points when all we're really looking at is the difference between the initial and the end point. So at this point, to continue my informal analysis here, maybe this has an x component, or a component in the x direction given by x, by some small notational abuse here. And maybe it's got a y component. Notice that we could either walk x units along the x-axis and then up by y units, or we could walk y units up the y-axis and then over x units, it would still get us to this endpoint xy. And so what we're going to do is we're going to associate with this vector, who I'll call u for now, a component notation. So if you view your vector as an arrow with a initial point at the origin, the point that it points to will be its coordinates. And we would call this component notation for the vector. I'll just call these components for right now. Now, one thing to point out is that there is a special point on each one of these grids, and there is a special vector associated with that point, namely the origin. All of the other vectors have a direction that they point in and a length which is non-zero. The only vector, right, this we'll call 0 the vector with a little vector notation on top to indicate that that's not just 0 the scalar, they are different, right, is the only vector with 0 length, 0 the number in this case. It is in component form 0, 0 for these two-dimensional vectors that we are looking at. And that's why it's not 0. It's a 0 in each slot. How many slots are there? What is the dimension of your vector space, right? That they're all zeros, right? Not just a single 0. And one thing about the 0 vector is that it points in no direction. And here I don't mean no like it points in 0 direction. That doesn't make much sense. Doesn't point along the 0 angle. That would be along the x-axis. No, it has empty direction, undefined direction. Another way of saying that, right? It points in no direction, or its direction is undefined, right? It simply is this point. But still, when we come to talk about how we're going to add vectors together, what it means for two vectors to be the same, equal to one another, or different from one another, understanding the 0 vector is going to be really important. So we want to talk about addition. Specifically, we want to talk about the addition of two vectors. Let's say we are in R2 still, and we have component form of a vector, x1, y1. And let's say that there's another vector also in the same R2 plane, and its components are x2, y2. Then if we wanted to sum these two vectors, we get a third vector. So this is a new vector. And what is its component form? Its component form is given by the sum of the coordinates. Sort of the most natural thing you could do when thinking, hey, how am I going to add 2 points together? 2 points not on a line. 2 points in a plane. How do I add them together? Well, couldn't we just think maybe we add their 2 components together and see what happens? And what happens geometrically is pretty cool. Let's draw a picture. Let's say my u looks like this. Here's his x1, y1. And let's say v is down here. Let's say this is x2 then, and this is y2. Then our u plus x we can sketch in the following way. Notice both of the x components are positive, and so their sum is going to be some larger number than each one. And notice that the y component is one negative and one positive. The negative one seems to have smaller magnitude, so their sum is going to be something smaller than y1, but still positive. And that gives us enough information to sketch the vector u plus v, whose component form is just x1 plus x2, y1 plus y2. Now, there's 2 geometric interpretations of what's going on here. One is that you are transporting this vector down to the tip of this one, and then tracing it parallel. Another is that you are translating this one to the end here, and transporting it parallel. So what can we see from that simple diagram is vector addition. Let's maybe even remark this. Note, vector addition is commutative. It doesn't matter what order you do it in. And that's precisely because this geometry is a sort of commutative process. It's symmetric. It doesn't matter which path we take first. We still wind up at the same end point. And that ties together with the algebraic commutativity of the components. This definition of addition, which here we're talking about the addition between 2 numbers, 2 one-dimensional vectors, if you will. That's simple. We know how to do that. That's basic addition, right? And that's commutative. So it shouldn't be too surprising that vector addition, right? Addition between 2 vectors is also commutative. Okay. So this is sometimes called tail-to-tip addition or tail-to-tip concatenation. Something to remark on here is that this is an operator. It takes in, it is a map from our vector space back to itself. It takes in, addition, takes in 2 vectors, say u and v, as its inputs, and it outputs this other vector, u plus v, right? Itself some kind of vector in our vector space. So it takes in, just like you take in 2 numbers and you add them, you get a number back. That makes that addition operator. Here we took in two vectors and it gives you a third vector back. That is a vector operation. But nobody writes it like this. This would be silly, right? People generally just use a plus sign and expect you to know the difference between vector and scalar addition. Okay, so I keep saying the word scalar. Let's talk about that, because now we want to talk about scalar multiplication. The word scalar comes from the idea of to scale something, meaning to proportionally size it up or size it down, maybe even negatively scale it, which would mean to reverse something about it. Scalars are going to be numbers for us, real numbers specifically. But in general, they could be any field element. So a field is just a place where you can do addition, subtraction, multiplication, and division, as long as you're not talking about division by 0. As long as you can do those operations and you have an identity element for each operation, you are in a field. We'll talk more about fields in some algebra video of the future. But for right now, our field that we're going to use for all of Calc 3 are the real numbers. So I won't talk more about like what those could be, except for maybe a little bit at the end of this video. And so what we're going to have here is not an operation from vectors plus vectors to more vectors. We're going to have an operation from numbers times vectors is another vector. Still, we're going to get a vector as an output. So again, let's declare a vector. Let's say u, and let's keep this in R2. We'll say this is a coordinate of two real numbers written in vector component form. And then let's have C. C can just be any real number. So remember, this is a set theoretic symbol that means this is an element of this. C is just a real number, whichever one you want, but he's fixed. Then how do we write CU? Well, this is just going to be in component form, C times each component. Again, we're trying to do the simplest thing we can to extend our notion of algebras to a question about, what do we do with lists of numbers now? And in the case of, well, I multiply by a number, what's the easiest thing we could do? Multiply the whole thing. Distribute it amongst all of the coordinates and have that be your new symbol. Okay, so what does that look like? Let me actually draw it over here. A little bit more room. All right, so let's say we start with some vector u. He's got components x and components y. Then if I multiply by, say, 2, this will multiply x by 2, and it will multiply y by 2, and that endpoint will be the endpoint of 2u. Try not to lose my original u as we go through this. If we were to take it half of that, what about 1/2 of x, 1/2 of y? Well, then we'd get 1/2 u. same direction. Notice that direction hasn't changed. Scaling doesn't change direction per se, it just changes magnitude. The reason that I put that per se in there is because it can change the direction in the sense that it can make it anti-parallel or parallel to the original. So anti-parallel is a special term that you hear for rays, like these sort of indicate rays or partial segments of rays. Anti-parallel just means going the other direction but still parallel. So for example, what if here we had negative x, and here I had negative y? Well, then minus u would go out the other side, right? This is the same thing as minus 1 times u. And that brings up something pretty important, which is that if you take a look at what is the difference of these two things, what about the difference of two vectors? Well, we can now do that by combination of scaling and adding. So let's look at that a little bit more in detail than I put in the notes. I think this is a good inclusion. So what about the difference of vectors? Right? What does it mean to say u minus v? And what does that look like geometrically? Well, algebraically, it's not going to be any different than taking u and adding the scaling by minus 1 of v. You can always rewrite subtraction that way. And minus 1 times the scaling of v is the additive inverse of v. If you added v and minus v, you get 0. They are anti-parallel to one another and have the same length. So let's see if I can't draw what this might look like. Let's say we had u, and let's say we had v. Then minus v is going to be down here. Anti-parallel, same length. And what does it mean to add two vectors? It means we're going to take this one and put it on this guy's tail and parallel transport it, right? Slide it, keeping direction the same until we get to here. This is minus v. And so this vector here that points to this new endpoint is going to be u minus v. Now, just like regular subtraction isn't commutative, right? 2 minus 3 isn't the same as 3 minus 2. Neither will this be. Because if I looked at minus u instead, right? Maybe that's something that looks a bit like this. And we did that backwards from v, we'd get something a bit different. That would be v minus u. But you can probably see from the diagram that there's a relationship between u minus v and v minus u. Take a moment, think about the geometry here. Try to answer that. What is that relationship? Well, they are negatives of each other. And this, of course, would make sense if we knew that minus 1 distributed to both terms and that addition was commutative so that we could reverse the order of things as we like. Another thing we should talk about is in what sense do we have equality of vectors? I lost my blue pen. There we go. We're going green. Equality of vectors. So we might even ask what we meant by equality of numbers, right? A number u would be equal to a number v if and only if their difference was 0, right? No difference is the same as saying two things are equal. And this is going to be our understanding of vectors. Two vectors are equal if and only if their difference is the 0 vector. And this is, again, why it would be so important to talk about the 0 vector. If we are talking about components, right, when are the components going to be equal to the 0 vector? When they are each themselves 0. So, for example, if I said, let u be equal to x1, y1, and let v be equal to x2, y2, then then u would be equal to v if and only if the difference between these two numbers was 0, which means, x1 was equal to x2, and same time simultaneously, y1 is equal to y2. And if this was a longer vector, then you just have to have equality of the components in a longer chain here, z1 equal to z2, and so on, in order to say that two vectors were equal. Where did that blue pen go? Oh, well. Oh, there it is. Now I have 4 colors. I'm unstoppable. Okay, so now I'd like to talk about some of the other intuitive notions of a vector that you'll see. We talked a lot about vectors at the origin, and we can get back to this concept of vectors at the origin, even if they were to give us, say, directed line segments. So let's take a look at that. So here we're talking about vectors from directed line segments. And so a directed line segment is one that has an initial point. Let's say this is at x1, y1. And a final point. Equal to x2, y2. And now these need not be at the origin. They merely indicate 2 points in space. Again, we're using R2 for easy illustration, but R3, you just basically add another component to each one of the operations we're talking about. And so we define this arrow, this vector, as the vector of line segment, directed line segment PQ. So this is going to be equal to the difference. This component is its horizontal length. This is going to be the difference of the order matters here, x2 minus x1, the difference of the x coordinates, and then y2 minus y1, the difference of the y components. Okay. So when you're using this definition, I just want to remark again that you need to have a bit of care about equality, because two vectors might not look the same here. They might be depicted differently, but if you were to just draw one that was parallel but had the same length and the same direction, these would be equal as vectors to each other. So let's do a small exercise to sort of see at least that that follows from the definition of how we create a vector, how we create this arrow by a difference here. So let's say I have some P1 which is at the origin, and some Q1 which is not. And let's say I have some P2, some initial point, which starts off the origin somewhere, and some Q2, its terminal point, which does not. Let's graph these to see what that kind of looks like. So here would be line segment P1. Or P1, Q1, the vector, shall we say. Get this out of the way. And if we drew instead P2, I would start here, 2, 3. Right? And this would be our P2, Q2 vector. And if we looked at their component form, then P1's, P1, Q1, would be equal to 1 minus 0, 2 minus 0. Which is, of course, just equal to 1, 2. However, P2, Q2 also has the form 2 minus 1, 3 minus 1, which is also equal to 1, 2. And so if they are parallel and of equal magnitude, they're going to wind up having the same component form when we write their differences as vectors. So because of this, also notice if you slid this one to the origin, they would eclipse totally, and you really would have them being equal as vectors if and only if they were equal in their depiction. Here you have them in two locations, but they are equal as vectors. This is an important thing to internalize, that they need not be the same if we're not choosing common initial points for all of them. They need not have the same depiction in order to be the same as vectors. So now we can talk a little bit about what a vector is formally. Because to formally define the vectors, what we do is we describe the properties we want them to have. And we say that a vector space is anywhere we have all of these properties. And then vectors are just elements of this vector space. So at this point, you can probably, if you're not interested in taking this beyond Calc 3, you could, or at the very least up to linear algebra 1 and 2, you can probably fast forward. But this is important because when we talk about a vector in mathematics, we're not always talking about a directed line segment. Right? That's a special case, and it's really helpful for Calc 3 and for physics in general. But vectors can be even more helpful as long as we, excuse me, vectors can be can serve other purposes, right? If we are sufficiently general in our definition of them. So I need to reload something. So we need a field of numbers. We need a set of elements called vectors. And in general, we would say F, just some field. We're going to consider this to be reals for all of Calc 3. And even in a large general space of vector spaces, we're interested in scalar values, which are real. We might also be interested in complex numbers. We might be interested in scalars, which are special subsets of matrices. But if you want to just think of them as a number, that's fine. It's a number where we're allowed to do addition, subtraction, multiplication, and non-zero division. That's a field. And two operations. Vector addition and scalar multiplication. And then they need to have a set of rules that these elements must obey inside of these operations. It's a better way to say that. That there has to be a certain set of properties which these operations on the field and on the elements of the vector space have to obey, have to correspond to. Let me start writing down a few of them, and I think it'll be clear what they are and how we can be sure that in our case for directed line segments or arrows or what have you in Rn, they are obeyed. They are completely obeyed. So not just that it exists, right, that u plus v is an element of our vector space v for all, I'm going to write the set theoretic versions of some of these symbols, for all u and v in V. And C times U is in our vector space for all C in our field and U in our vector space. Together, these are called closure. Closure under scalar multiplication and vector addition. This backward Z is there exists, or there is, or there are. This one means that there's a unique one. There exists a unique element, the zero element, in our vector space, such that it does not change the vector u to add it to the vector u. Similarly, there's an identity in the field such that, and I believe we could say that this is a unique identity, although I'm not terribly sure about that, so don't hold me to that one, that there's a unique element, the one element, whose scalar product with a vector is itself. So now we're going to talk about inverses, which are special vectors which can take us back to one of these special elements. So for example, for all u in the vector space V, there exists an inverse of u in the vector space V such that u plus its inverse is the zero element. And that'll be all I want to say about that. What other properties do we need to obey? So our addition element needs to be commutative. Or our addition operator needs to be commutative. Order of addition cannot matter. It needs to be associative. So the order of execution cannot matter. And there needs to be, we have inverses, we have zero elements, we have the identity. We have to have associativity with scalar multiplication, in the sense that if I have A times B times U, this needs to be the same as A times B, then times U. And finally, we have two distributive properties. if I have A times U plus V, this has to be AU plus AV. And if I have A plus B times U, this has got to be equal to AU plus BU. In other words, we have to be able to factor around sums of vectors, and we have to be able, or distribute, right? Factor out a scalar product from a sum of vectors is going the other way. Or we have to be able to factor out a vector. We have to be able to distribute within a scalar sum. This isn't a vector sum, this is two numbers summed together, right? So we need to be able to distribute one way against one kind of addition and the other way against the other kind of addition. Now, here's the thing. Here's why I bother with all of this. Any space that does all of these things, any set of elements that's closed under a kind of addition, has a field that's closed under that, has a 0 element, has a 1 element in our field, has inverses of vector addition, is commutative, associative of scalar multiplication, distributive in these two different ways. That's a vector space. Any element in that set is a vector. So as long as you just have these rules obeyed, you're talking about a vector. And that is the full sense in which you can approach vectors in general. It's just things that obey these rules, these very simple algebraic, you've known them since grade school, rules. So as you might imagine, that's a huge space of things that we can eventually talk about with vectors. So there's one more thing I'd like to conclude with, and then we'll talk about some exercises you might try, and that is length of a vector. So the length, also called the norm of a vector, is given in this way. Let's say that we have in component form some vector given by xy. Then the norm of this vector is the length of the corresponding arrow. And as you might imagine, this is going to have something to do with the Pythagorean theorem. Because we know that this length squared is going to be equal to the sum of the squares of the components. So that will be the square root of x squared plus y squared. If we were to put this in a different context and say that this was in fact a three-dimensional thing, well, it's a nice exercise to show that in 3 dimensions, all you need to do is look at the sum of the squares of the components again, and take their square root. This is the 3-dimensional version of the Pythagorean theorem. And as you can see, if we have some w equal to x1, x2, and so on, so this is all the way to xn, then if I want to know its norm, this is now an n sum under this product. I think the easiest way to write that is like this, where we square the elements, sum them, and then square root them. That's the Pythagorean theorem in n dimensions. And this is how we're going to talk about the lengths of vectors, is by calculating this norm. So as a quick application, oops. What about unit vectors? That's when your length of this thing is equal to 1. So if I tell you any vector, let's say let's say v instead, equal to 1, 2, or better yet, let's get something I know is a Pythagorean triple. Let's say 3, 4, right? And we could ask, well, what is the length of v? And this would be, well, the sum of 3 squared plus 4 squared, which you can work out as 5. And so how could I make a unit vector, right, which we sometimes write v hat, right, is the unit vector in v's direction, right? This would be v divided by the norm of v, or better yet, 1 over the norm of v times, as a scalar number here, times v. So this is a scalar product being taken. And in this case, that would be 1/5 of 3, 4. That's 3/5, 4/5. And just to try to illustrate that a little bit, what happened here, we had some vector at 3, 4. And now we have a vector at 3/5, 4/5. So divide by 5, that's something less than 1. So you can see it's similar in the sense that the ratio is the same. But if we were to draw the unit circle, that's a little bit too close for comfort there, but it would lie on the unit circle. Maybe that's not a great illustration, but I think that's where I'm going to leave it. So let's say you want to find some vector that has length 1, the so-called unit vector. What you're finding is a point on the circle that is pointed in the same direction as the original vector. So this would be v, and this would be what I called v hat right here. Okay. So I'd like to conclude these videos with a suggestion of exercises. So let me write those on the board now. They should be easy enough that you could get them. If you have a hard time with them, leave a comment and I will try to get back and give some answers or some assistance. But let's let u be equal to, so number 1, let u be equal to 6, 1, v be equal to -2, -3. And now tell me the following things. What is u plus v in component form, right? I want the component form. What is 4u plus 2v? What is -u minus v? Number 2, let's do this in 3 dimensions. And let's first do some more linear combinations. These problems will get harder as I go on. That's okay, keep pushing. Make sure that you understand this bit completely, because all of our manipulations of vectors in the future are going to just take this for granted. So make sure the distributive property makes sense to you. Make sure all of this makes sense. Can you use like terms in these? Yes, you can. Here's a slightly harder one. Find a new vector such that either u plus v plus w is equal to 0, or 2u plus 3v minus w is equal to 0. So we want to find a linear combination, some w such that this linear combination becomes, the 0 vector. That should be a 0 vector. And finally, let's say u is equal to the set of all ones in Rn. So there should be, this is my x1, this is my x2, and so on all the way up to xn. What is the length of u in terms of n? It is important to do this praxis. You have to do the practical exercises in order to start to understand the patterns at play. So don't skip this part. Thanks. I hope this has been helpful. Please email me any questions that you might have. Please look in the video description for the full set of notes that these lectures are based on. And have a great rest of your day. Good luck with your studies.